Should be good now. Okay. Hello, everybody. Thank you for attending Astronomy on Tap Köln, our event number 11. As of tomorrow, we will have been streaming for 1 year. So we are fairly happy to be lasting this long and all of it completely online because launched during a pandemic. So today we're joined by Lucas Labadie. He'll be presenting on some very nice planet formation and very high resolution observations. And then after the talk, we will have some news presented by Parit as normal. So please stay for that. But for our first presentation, Professor Labadie, well, going all the way back, I guess you had your education in France, in Marseille and Grenoble, and then you had 4 or 5 years of postdoc in Germany and Spain, and all working on instrumentation, I guess, for all of this, these observations that you're going to be mentioning today, and the intersection between observations and, or the astrophysics and the instrumentation. And for the past decade, you've been a professor here at Universität Köln. So I'm very excited for what you have to present for us today on planet formation. You're welcome to share your screen when you are ready.
So you're well informed, so I don't have to present myself. Okay, let me share that. Okay, you should have it now. Here, can you see it?
Yes, it's good.
So I just select spotlight, and yes. So thank you very much for the introduction, and okay, for having me here. Indeed, so I'm Lucas Labadie, based in Cologne, and I would like to discuss with you guys today a little bit about planet formation, in particular on how we witness that. And that's why I called that a sharp view on planet formation with high angular resolution. This is a topic that both in instrumentation and on science we are interested to work on with my collaborators here and also abroad. And what you see here in the background is just a view of what is called the VLTI, so the Very Large Telescope Interferometer. This is composed of at least 4 large 8-meter telescopes, and aside them, so you see them here, they are opened, you know, pointing, and beside or just close to them, you see some smaller telescopes, which are called the auxiliary telescopes, and that can move around. So they can move around because you can do interferometry with them. Whereas the other one, you can do interferometry, but you can also observe as normal single dish telescope. So today I will not dive extremely deep in the instrumentation, but I would like just to give an overview of what is been doing at the moment, I mean, the community regarding planet formation. So the first thing that we would like to say, of course, when we talk about planet formation, there's the word planet inside. And, you know, so the question was, so do those planets exist? Are they here somewhere? So, I mean, you have to know, probably you know already, that this is a very old idea, right? So, I mean, people already centuries ago were talking about these ideas, writing about this idea, having no clue about this, if this was existing or not. And I'm just showing here a book, which actually is a French book, which is called Entretien sur la pluralité des mondes, which was about essentially potential world that they had no idea about. So there was this nice sentence: fixed stars, there are so many suns, each of which enlighten other worlds. So this is translated into English. Actually, the text is in French, but I think that's better for the understanding. Voltaire himself, of course, I mean, had novels about, you know, people on other planets with micromegas. So that was, as I said, an old idea. But in the meantime, of course, then many decades have passed. I mean, and now we know that those exoplanets exist. I mean, you may know so that like 1 or 2, I mean, actually in 2019, the Nobel Prize was awarded also to those 2 famous scientists, Michel Mayor and Didier Queloz, because of their discovery, the first discovery of an exoplanet. And here, what I just want to say, I don't want to dive very much into exoplanet themselves. I just want to show you with the central plot that actually a large variety of planets have been discovered so far, with many different properties in terms of radius, masses, separation with respect to the host stars. Some of them were also characterized spectroscopically. And also, of course, this diagram, so you see here a lot of the yellow dots that have been discovered by Kepler. This graph might be biased actually, because of course this parameter space is being explored, and we may have actually an Earth planet or even a smaller one at large distances, so which has not been yet discovered because the technique did not allow that to do so. So this is a field that obviously is very active. And you see here on the left, actually I have to move a little bit in my window because otherwise I don't see. You see on the left here, just a second, okay. You see on the left an example of directly imaged planets, which have been imaged back then. So you have on the right, top right here, the famous system HR 8799, where here you see actually 3 planets, although by then a 4th planet closer to the star had been discovered. And you see here on the bottom, a view of the planet Beta Pic B, Beta Pictoris, which is obviously orbiting the star Beta Pictoris. And you see it here, that's been detected also by direct imaging. And what also is interesting here is what you see around it. You see this big halo of dust. Well, this dust here, actually you see big halo of light, which is to be connected with the dust that is actually existing and orbiting around this star. So this is actually a disk. Turns out there's a little bit older disk, probably close to a debris disk, which is present in the Beta Pic system. And of course, the question is how much there is connection between these planets and the surrounding disk. So that's why when we continue a little bit the historic view, one has to know that basically the idea that planet would form somehow out of a sort of nebula is also something which is relatively old. That was already introduced by Kant himself, back in the 1700s, as well as Laplace himself. So where they were proposing, of course, based on no scientific ground, but they was proposing that basically a sort of nebula, they had no idea what that could be, would kind of contract over time and, give birth to some planets. So that was very, almost poetic, but it was it is somehow interesting to know that people thought about this already, many centuries ago. So when we think about planet formation, it could be that, disks are also an important quantity or an important object to consider. Well, what are those disks? So maybe let me introduce briefly what we're talking about here. Here, what you see is a general view of the Serpent's molecular cloud, okay, where you have like different stars, so the star-forming region, which is relatively far away, 230 parsec. It's relatively young, of course, between, around 2 to 5 million years. And this is a stellar nursery, okay, so where actually stars are being formed. But star formation and planet formation are actually relatively intrinsically connected because, they go somehow a little bit together, in particular through this object that we call the protoplanetary disk. And here, if we base ourselves on the different, I would say, surveys, you can identify in that picture many objects that turns out to be what we call young stellar objects, okay? Meaning that there are objects like stars, there are objects that have a central star, which has not yet reached the main sequence. And this star is surrounded by some material, gaseous and dusty material, which produce infrared excess to the stellar light itself. And that's how typically we can recognize, we can see actually those objects, those young stellar objects. So these ones, as you see here, you see the scale, this is very coarse image. Actually, each of those objects, they measure in size, maybe, 200-300 AU across. So we don't have much detail here. We have a nice image of the whole, cloud, okay? But we don't know much about the individual object if we do not really focus on them. So we know their SED, also spectral energy distribution properties, so how much they radiate in the infrared, but that's it for the moment. Just looking at that image. So with this, I would like to introduce a bit what the disk is. So here in the central image, what you see is a simplification somehow of an object that is relatively complex, the protoplanetary disk. So I will have to make some simplification because, I mean, I would not have time enough. I mean, you need a lecture to explain or several lectures to explain all what is happening in those objects. But basically, this gives you an interesting picture of what a disk is. So you have on the left a central star that is somehow, by different mechanism that I will point out later on, is accreting material from the disk onto the central star. Essentially, you have an exchange, you have a, let's say, a modification in the properties of the disks that allow basically transport of material on one direction and transport of angular momentum on the other direction, which means that basically matter from the outer disk that you see here could be accreted onto the central star. When we look a little bit more in detail to that disk, we see that actually we have essentially two regions. You see that here I show what is called the pure gaseous disk. So that's a region of the protoplanetary disk where you are essentially dust-free, because the dust here is being evaporated. It's basically too hot up there to allow the dust to survive. Around 1500 Kelvin, it would evaporate. And then behind this, you start to have the presence of a dusty disk, which is relatively complex in its structure, much more complex than what is shown here. So here it looks like a flared region, flared essentially because the disk is in hydrostatic equilibrium, the same way our atmosphere here on Earth is in hydrostatic equilibrium. And then you have here the planet forming region where we think that actually planet or smaller planet may form. This is still something that is not very well known, where they form, at which time, and how they actually migrate inwards. There's a lot of theory, but I mean, many of them are still very much debated. So this picture here can be very complex. What I'm not talking about here is all the viscosity that you have in this disk due to the presence of the gas. So most of the mass here is in the form of gaseous material, whereas the rest is, dust. So small dusty particle, which are just a small proportion of the mass, but still that contribute very much to the infrared excess that people observe. And this you have a temperature distribution here across the disk from the inner region to the outer disk to the outer regions, where basically you go colder and colder. And that's what you see here with those small spectral energy distribution that are shown. The red line here shows basically the contribution from the star and from the disk. So the star is the blue line here, and the disk is the red line. And basically, as you go to longer and longer wavelength, you start to be dominated by the emission of the disk itself. So this disk is actually an important element, as I say, because it can feed basically planet formation, or at least that's what we believe it can do. And there are good reasons to believe that this is indeed what is happening. So those disks actually interact with the planet itself. So there are different scenarios which are invoked. I will not detail them extremely in detail, but what we talk about here are essentially scenarios that are called core accretions, where basically you build up over time in the disk by aggregation, you build up a core, a planetary core, which then become massive enough to accrete gas. And that's a little bit what you see here in this hydrodynamical simulation. You see that basically as the planet is accreting mass through, for instance, those flows here, it will also start to interact with the disk and form over time larger and larger gap. In particular, if the planet becomes massive enough, it will really clear the inner region of the disk and end up basically in a sort of cavity where you have an inner disk that is surviving here and that will disappear over time, certainly. And you have basically a planet that is present here, still accreting material. So that's one of the ideas how those planets can form. There are other ideas. So for instance, what we call disk instabilities. So this, maybe some of you are already familiar with that. It resembles more or less to star formation. So star formation, you know that this happens by cloud, collapsing and fragmentation because of their own gravity. And this is also a little bit what may happen or what people think may happen to form planets. Actually, this model or this, let's say, scenario has somehow some complication anyway, because basically it would work only with very massive disks. Only very massive disks would be sufficiently gravitationally unstable to kind of collapse and or to fragment and form those cores, a little bit like what happened in the process of star formation. So those two models, let's say, are a bit in competition, but in the end, I mean, it doesn't matter that much. We know that those planets that they form may actually interact with the disk. And that's why we know that the disk structure is far from being very simple and smooth. It has to be something that is probably complex, as we will see. So here in the next slide, you see a little bit the process, I mean, what we think the process of planet formation could look like. So we think that actually we know that disks exist, no doubt about this. We observe them, and we know on the other side that planets exist. We detect exoplanets. What happened in between? So how you basically go from very small particles that are, you know, micrometer or sub-micrometer size particles that are going to stick and to aggregate with each other to form larger bodies, you know, from meter size up to kilometer size. So you will have several order of magnitude to overcome before you can actually form actually a protoplanet, or at least a planetary core, which is massive enough so that it can accrete gas on it. And this process here is still not well understood. What we knew so far is that disk, as I say, disk exists, planet exists, but now we are understanding little by little a bit better, or we think we understand a bit better how this planet formation takes place. And I can give you a very simple example. I mean, when you think about snow, for instance, you have all experienced that, you know, when you have fresh snow, okay, actually it sticks very, very well with, you know, you can make a ball actually very easily. Well, actually, it turns out that even in disk, you have ices, you have like cold material that may help basically the matter or the dust that is in the disk to coagulate and to form basically larger and larger bodies. So that's a little bit simplified view, but this is what happened. And this process actually has to be fast. It has to be fast because actually the disk itself is short-lived. Short-lived, it means that whereas stars can live, you know, on the main sequence for billions of years, the protoplanetary disk itself evolves quite fast. I mean, on a time scale of about 10 million years. That's what you see, for instance, here in this nice cartoon here, where you see for different star forming region, the disk frequency as a function of age. And you see that basically this frequency actually diminishes dramatically as you go to older and older star forming region or older associations, where basically the disks are less and less frequent because they have been actually dispersed either by planet formation, by photoevaporation, by a multitude of effects, including accretion onto the star, that makes this intrinsic body, I mean, this body is intrinsically not very, I would say, stable. You know, of course, it's in Keplerian rotation around the star, but actually it would lose angular momentum and therefore it will drift inward and it will be accreted onto the star. It will be photoevaporated by the very intense UV radiation from the star and so on. So basically the message to remember is that this is short. So you have to do it quick. So is it possible, I mean, being so quick to witness one of those planets being forming? I mean, that's what people have tried to do. And for this, you need to have actually very high angular resolution. Why? Because, I mean, if you think about the human eye, I mean, the human eye has more or less like 0.02 degrees of angular resolution. Okay, and what you need here, you need to look at a region which is 1 to 10 astronomical unit wide region at distances which are on the order between 200 400 parsecs. Okay, so it is similar to see the detail of a football. I mean, we are in the Euro at the moment, so to see the details of a football pitch on the surface on the moon. I mean, with the naked eye, you have 0.02 degrees. What you need is 0.00001 degree, 1 to the 10 to the minus 5. And this you can do with large telescopes, of course, like the one that we have, the VLT. But of course, you cannot only do that with a telescope itself. I mean, the resolution is proportional to lambda over d. It means the bigger the telescope, the better you will detect or you will resolve your object. But we have a problem from the ground, is that we have atmosphere. And what atmosphere does is exactly what you see here in this movie. So it's a fluid. The atmosphere is a fluid that is turbulent, very turbulent, and basically really deforms actually the view that you have of your object when the wavefront goes through the atmosphere. That's exactly what happens. You don't see any detail of the, €1 coin. No way that you can detect, the shape of Europe and this kind of thing. Well, there is a way to improve that, is to use adaptive optics, in particular on large telescope like the ELT, on which we are working on with our group. And the adaptive optics gives basically this result. So here you see something, a blob, where you don't see much more than, spherical or like circular distribution of light. If you can compensate basically for the atmospheric turbulence, you will start basically to resolve the system, and you will be able to detect actually faint companions which are close to the star. Those faint companions could be brown dwarfs, could be planet, could be disk structure, whatever you need. But you will need this technique in order to detect those structures at the resolution I was talking about. We want to look at 1 AU at 400 parsec. And sometimes this is not sufficient. We need to have access to even larger resolution. And this is what you can do, for instance, with the VLTI interferometer or with the Alma interferometer, which works on the same principle, so that basically they synthesize somehow, to make it simple, they synthesize a telescope that would have the equivalent diameter of the longest baseline. So for instance, the VLT, the longest baseline is about 200 meters. So you reach a resolution of lambda over 200 meters, which can be 10 times or even 50 times better than what you get with a single dish telescope. So this is done typically in the infrared or in the sub-millimeter region of the spectrum. So this is what people are doing. And, here you see now an example, a collection of those protoplanetary disks which have been imaged with adaptive optics, in particular with an instrument which is called SPHERE at the VLT. So there's a lot to say about that image. So let's just go to some more important messages. So first of all, these are obtained in scattered light. So this observation takes usually place around 1 micron, 1 to 2 micron. And what you see here is not the thermal emission of the disk. So it's not really the temperature of the disk. You see the light of the central object, which is scattered by the surface of the disk. And by this way, you can actually evidence the presence of the disk if you have a good image quality enough, and you can even see very different structures. So for instance, you see a lot of those spiral structure as we saw in the simulation. We see somehow the presence of some rings or gap. We see that also we have asymmetries, radial asymmetries. Not all the disk seems bright at the same location if you look at different azimuth. And this points out basically the complexity, the intrinsic complexity of the disk distribution. And when we look at sub-millimeter wavelengths, so that's even more interesting. So this is the result from Alma. So Alma looks at somehow 1 millimeter wavelength, roughly. Okay, so here you really see the cold material of the disk. And these are like spectacular images that shows that actually the disk is not at all what people thought like 15 years ago, like a very simple, regular kind of pizza around a central star. No, it can be very much structured. And it could be structured by planet formation, for instance, but not only. So it was clear that those objects, they present more and more gaps and complex structure, that not all of them have to be or can be attributed to planet formation. You see, for instance, here sometimes you have some asymmetry also in the brightness distribution, which could be potentially linked to dynamical effects, but I mean, it's not a one-to-one. So that's why it's very important to have those different images. So in the near infrared, in the mid-infrared, and in the sub-millimeter, these are very rich images. So if we continue and basically go a little bit towards, kind of conclusive remarks somehow, I would like to go now a bit more in detail of some particular objects. So that was, for instance, 2019, the first detection of actually a forming planet or a protoplanet in the disk of a young sun analog. So basically, this is PDS-70. This is similar to our sun, but much younger. Okay, maybe it looks like how our sun was like when it was, 10 or like 5 million years old instead of the 5 billion it is now. A very mature system. And then in that disk, harbored in that disk and carving somehow the disk itself, a planet, a protoplanet, actually a warm protoplanet was detected. It was detected thanks to adaptive optics, and it could even be characterized. So it is basically a planet that is still quite hot. and therefore bright in the infrared. So that's why you detect it here, and is actually on the order of few Jupiter mass and still kind of accreting matter on it. How do we know that this planet is still accreting matter? Well, there is a tracer you might be familiar with, which is, so here you see an example of the spectrum that was detected for that planet. But if you look at actually accretion tracer that maybe some of you are familiar with, like for instance, H alpha. H alpha in astrophysics is a typical accretion tracer. You trace basically hot ionized gas that are in phase or that being accreted onto the central star. And this is what was done here with that planet using an IFU. So an IFU is basically a 3D spectrograph. So instead of having a simple spectrograph where you have like flux versus wavelength, which is what you have here, you have like flux versus wavelength. What you have image versus wavelength. And at the position of the H alpha line, actually you could detect the presence of H alpha ionized gas at a particular spatial location. And it turns out that the location of this H alpha accretion was concomitant with actually the PDS-70 planet. And actually, there's not just the one planet that was detected through accretion traces, but two planets. And by then, so PDS-70 was found to have actually 70b and 70c. So this is a very powerful tracer. And here you have also I would say the counterpart in the submillimeter, where you have the position of 70b and 70c, and around it, you see the massive cold, or let's say cooler disk, which is surrounding the object, and which is very bright in the submillimeter. Because remember, at that wavelength, you look at a wavelength range where typically you trace material which is on the order of 100 Kelvin, has a temperature of 100 Kelvin. So you wouldn't see that at very short wavelength in the near infrared. That's the powerful of going to those longer wavelengths. So this is a very important image that compensate, or that, let's say, goes and confirms basically the presence of forming protoplanet in the disk of PDS-70. And we have here, just to close on that, another example, more recent events. These are like 2020 result with, for instance, abeorica. So here, this is also an image that was obtained through adaptive optics, where actually you see the very complex structure of the disk. You see also the spiral arms in all directions. And actually, so I don't have the time here to detail very much, but one of those structures has been followed and is believed actually to be another example of one of those accreting protoplanet in the disk of abeorica. So here you have the counterpart in the submillimeter, where you also find, or you also see those arches, those arms, those spiraling arms that actually are driven or possibly driven by dynamical interaction between this planet and the disk itself. So in other words, what I want to say is that if you can know something about the disk and the details about the disk, you can know something about the detail of the planet. And just to go even shorter or even closer to the star, what is possible to do also, in particular here, you cannot do that just with adaptive optics, but you need interferometry. You can look at even closer region, really at the interface between, I told you at the beginning, there is a region where basically dust is not present any longer because it will sublimate, it's too hot here. And you will be able to really look at the accretion process between the disk and the star. So why this is important? This is important because actually we know that those stars, the Loma stars, the T-Tauri stars, have strong magnetic field that actually strongly impact the processes of accretion. You see that on that image. Basically, what we call the magnetosphere of the star is going to shape basically the process of accretion. And one of the processes that is invoked, and which is actually even confirmed here by the result here we got with interferometry, is the magnetospheric accretion onto the star. So basically, all this is very much connected. The disk here on the outer part that is being dynamically interacting with the planet, but at the same time, the disk itself that is interacting with the star, and that will not last very long and will disappear at some time. And in that time scale, you have to form the planet. So you need to understand all those processes to understand planet formation. Just to finish here on the right, you see, for instance, at that small scale, much smaller scale than what we are talking here about. Yeah? Here we're talking about tens or like hundreds of AU. When you look at the AU scale, you see already here, in the case of, for instance, that star, which is interesting, is HD 139614, what we studied in the past, we form already at that, I would say, at that spatial scale, you form already some cavities. Some cavities where basically you have a deficit of gas and dust. Again, why? Well, I mean, a plausible explanation is the presence of a forming planet. Be aware that this is not an image, okay? This is a model, so we did not get an image on this object, at least not yet, maybe in the future. So this is basically an indirect measurement of the structure of the disk. And what makes this disk particularly interesting is that it's not only gapped or carved, but you have also relative tilts between the inner and the outer region. What can you imagine those tilts are resulting from? They can result actually from, again, interactions, dynamical interaction between a planet or several planets that may form in the disk, and that, of course, gravitationally influence the surrounding disk. So actually, this kind of misalignment they're getting, I mean, this is really fresh and, you know, recent science. I mean, people are witnessing this misalignment between the different regions of the disk more and more. So we are understanding through the disk better and better the process of planet formation. So I will conclude here with some take-home message. So you see in the back, again, one of those very nice hydrodynamical simulation where you see the effect of forming planet on the disk. So what we know is that we have, you know, old and mature exoplanets that are found to be relatively common around main sequence stars. That's what I showed at the beginning, thanks to, of course, Didier Queloz and Michel Mayor, at least at the beginning, like 15, 20 years ago, 1995. We know also that basically the planet formation is very much connected, or is thought to be very much connected to the properties and the evolution of the parent disks. And this is not even proven because we detect now young protoplanets in those disks. So we need to understand the disk to understand the planet. I mean, that's basically the message. And if you really want to do that, you need high angular resolution, because it's not sufficient just to understand, you know, the SED or the spatial energy the spectral energy distribution of the object. It's not enough to understand its spectrum. You really have to, on the long term, to go and understand those kind of structure. You have to model them. You have to propose simulation that explain how the planet or the forming planet interacts with the disk and so on. Why do you get gaps? Why do you get brightness inhomogeneities? Why tilts? What is the role of the accretion mechanisms and so on? So the high resolution, the very high angular resolution that you have with interferometry is really key here. So I think I will stop here because that I was asked not to be extremely long. So thanks for the attention, and I'm happy to answer any question.
Thank you very much, Professor Labadie. Very interesting presentation. To any viewers, if you have any questions, please post them in the chat and we will get to them. I have some questions myself, and I think there's some more from our committee, but first I want to address one of the questions in the video already. From Vladimir Kudryashov, one of our previous presenters, but he said it was about the angular resolution. Is there, would it be very useful to have 5 micro-arcsecond resolution? Or
okay, so it depends for doing what?
Yeah.
Okay, so I mean, let's go back to that typical, I mean, maybe that's a good image where to start from. I mean, having 5 micro-arcsecond resolution, yes, it's always useful if you want to look very far away. So the simple answer is that if you want to look at the inner region of a young stellar object that is, you know, kiloparsec away, okay, so the resolution will always help. However, resolution is not everything. I mean, you have also sensitivity. The more distant your object is, the fainter it will appear. Okay, so looking at very distant object with, I mean, 5 or 10 micro-arcsecond resolution might be interesting as long as you're able to see something. It could be that it's too far away. You need a telescope which is too large that you cannot even build in order to detect basically those objects and to detect the structure in the disk of this object. So basically you have to put that together. You have also to understand what process you are going to look at different spatial scales. So if we talk about, for instance, 5 microarcsecond resolution, it could be that you would like to detect actually rather than spatial, I would say spatial, how do you say, spatial features, you may be interested in detecting astrometric features. You know, for instance, you would like to understand how the planet or the central star actually moves because of the presence of the nearby planet, moves, and that could be an indirect measurement. You don't have necessarily to detect the planet. If you have a possibility to do very precise astrometry, astrometry is different from imaging. Astrometry is basically measuring the position of the star. If you are able to do that, well, you can also, in an indirect way, you can get information about what are the dynamical interaction of your central star with its surrounding. That's also a possibility. That's, for instance, what the Gaia mission does. The Gaia mission now is a very precise, very high accuracy astrometric mission that doesn't have very high angular resolution, but has a very high astrometric precision. And interferometry can help in doing that. Interferometry can, so for instance, be very concrete. The instruments like gravity that we are using, you can reach astrometric accuracies thanks to the very long baseline, astrometric accuracies on the order of 10 microarcsecond. So I think the microarcsecond scale is probably at the moment most powerful for astrometry. For imaging, it will be, of course, always interesting to have the highest angular resolution as possible. But again, I mean, you have to put that in perspective with which object you could observe at that resolution, how far they are, can you really detect them, and so on. So that's at least one part of the answer I would give.
Okay, thank you. The other questions on our YouTube video are from Alina. So I don't know, Alina, if you want to ask yourself.
Okay, thank you, Craig. Some of those questions are I collected and just posted it there. So the first question was from Rishi. He was asking us, why is Lagrange 2009 image so dark in the center? Is it because of the test or some other processing was there?
So can you repeat just the beginning of the question? Which one?
He mentioned about Lagrange 2009.
Okay. Yeah, very good questions. I'll come back to that. So I think that's the beginning. So I will explain all that. Just give me a second to go back to that. It's not always very fast. So the question is basically, okay, so that image, I believe, so the bottom one, why it is dark in the center. That's the question, right?
Yes.
Okay. Well, actually, this is a collage image. I will explain a little bit what was done here. So basically, in order to detect the planets, what people do is they use a technique called coronagraphy. So what is coronagraphy? I mean, in a nutshell, it consists in putting a mask on the central star to block most of its radiation. And in that way, to be able to see faint emission or faint object around it. So a good illustration of that can be imagined with the sun. Think about the sun. If you look like naked eye the sun, no way that you're completely blinded, right? Now, if you put a mask, I mean, you can do that with your finger. I mean, that's a very bad coronagraph, but it's better than nothing. Well, if you block with your finger, let's say the disk, the solar disk, then your eye will be able to accommodate and to see to some extent what is around the solar disk. Of course, with the resolution of the eye, there's nothing much that you will see. But if this is done a bit more precisely, using what we call solar coronagraphs, you will be able to see actually the sun corona. And that's why the technique is called coronagraphy. It comes actually from the fact that when a coronagraph is used, I mean, the original idea was to observe the sun corona. Okay, so it was basically a tool to observe the faint emission which is around our sun. Now, the principle works the same way. So you block the central star as good as you can, and you see what comes around. So here, actually now you can, of course, it's a little bit, as I said, it's a collage. The coronagraph here, I should zoom in, but the coronagraph is much smaller than actually what you see here with this dark area. what the coronagraph is on the order of the size of the star. I mean, angularly talking, of course, not linearly. So it blocks just the central star, and it allows actually to retrieve the presence of the planet around beta peak. The reason why it's black around is that basically what remains, you have what we call like speckles, or like residuals, which are much fainter, or which can be much fainter than the planet, or at least then they are processed. I mean, these are images then that are shown in, you know, like public outreach, or like, you know, press releases and somehow, and things like this. So this image here is a collage of all this, but the detection, of course, is real. The detection comes from the use of a coronagraph that has mainly been used to block the central star and detect the planet around. What you see around is the disk that comes from a different image. It's not the same image. This disk here has been obtained through another technique, also connected to high angular resolution imaging, but then the two have been put together a little bit in an artificial way to illustrate actually the presence of the planet. So the scales are correct. So it tells you where is the planet with respect to the disk. So the reason, again, to finish my answer, why it's dark is essentially because, I mean, most of the light here has been canceled out around the star, and then like further processing has been done in order to isolate the disk. Also, keep in mind that even to show to visualize the disk here, the same technique was employed. So basically, also a coronagraph was employed, but in that case, the coronagraph was larger. So you have to imagine that on one side, you put a large coronagraph to block the star and to see the disk. That makes the first image. And on the other part of the image of the collage, you have a smaller coronagraph that blocks the star to see the planet. And the two are put together. So that's the reason why at the end, the collage looks like this. Okay. And this is also what you see, I mean, basically in all those images here. Every time a coronagraph here has been used, you know, you see here this the central gray area. The central gray area corresponds basically to the typical size of the coronagraph, inside which you cannot see anything. You don't have the resolution to go inside this area, but it blocks essentially most of the stellar light, which allows you to see the disk. So that's the reason why it looks like this.
Thank you so much for the answer. And when you were talking about answering Vladimir's question, you said about something about baselines. Mm-hmm. So you said it's very good to have a very long baseline. So could you please explain what is a baseline for our audience?
Sure.
I believe like many of them may not know.
Yeah, absolutely. I mean, I have to apologize there. You know, I wanted to stay a little bit in time, so I did not detail that very much, but I will tell you something. So the big difference, so here you understand that on the left part, I mean, it's a little bit low resolution, but you have like a single dish telescope. So this, I guess I don't have to explain very much. People understand. Mm-hmm. Well, it's sometimes if you want to build like a 300 or like a 1 kilometer large telescope, I mean, it's not easy to make, you know, like a single dish telescope of that size. So what is possible to do is to use actually interferometry. So in a nutshell, what is interferometry? Interferometry is a technique where basically you do not rely necessarily on the size of the single telescope, but you rely on the separation between the telescopes or the antenna here, like on the left part, in the case of Alma. So you see that Alma here, the whole array here is called Alma, and Alma is composed actually of many antennas, each of them being, I mean, at least for sub-millimeter science, not that big. I mean, I think it's 12 meters or something like this, you know, so those antennas, they don't have intrinsically very high angular resolution. You would agree with me that it's the same formula applies. If it's lambda over d, you take sub-millimeter wavelength, you consider that the antenna has like 15-meter diameter, and you can calculate the angular resolution. It will be relatively poor. Now, with the interferometry, what you can do is that you can combine actually in a either heterodyne or homodyne way. That's a little bit, you know, a technical difference, but basically you can combine simultaneously the light that is collected by each antenna. So to make an example here, look at Alma again. The day they want to observe a source, the same thing will happen with the VLTI. The day they want to observe a source, all the telescopes are going to point towards the same direction. Okay, they will all observe the same source. And then the resolution of the observation of the image that you will get will not depend on the single antenna size, but it will depend on the baseline. And the baseline is basically, in that example, the longest distance that you have between two consecutive or two different antennas. So here, like if you see my spot, a baseline is, for instance, here the distance between this antenna and this antenna. It can be, several hundred meters or even kilometer if you put them, like far away enough. Here at the VLTI, that's the same story. You see here the small telescope here. The small telescope here has a size of about 2 meters, roughly. The mirror of the small telescope is 2 meters. So the resolution is not that big. But if you put like one of those telescopes here and another telescope up there, so here, basically you will have a distance of about 200 meters. Then the resolution here, that's why I try to say here, the resolution is not lambda over D, this is lambda over B. So the bigger the baseline, so the longer the baseline, the higher the resolution will be. So if you take lambda 1 micron, if you take B equal 200 meters, well, then you can calculate the angular resolution that you have, and you will have something which is on the order of milli-arcsecond, which of course you cannot reach just with a single dish telescope. Does it clarify what a baseline is?
Yes, it really clarifies. And thank you so much. I have one more question and then I'm done. So when you said about dust depleted regions in the protoplanetary disk, so do we know what is the physics behind which creates a dust depleted region? Or
so sorry, what is the, can you repeat the? Sorry,
dust depleted regions in the, so do we know the physics behind them or?
Yeah, absolutely. Absolutely.
Okay, could you explain?
At least, yeah, sure. Well, at least we think we know, as always.
Okay.
I mean, the dust depleted region is resulting from what I tried to illustrate with a simulation of the core accretion case here. So maybe I will come back briefly to that here, and I will advance a little bit. So basically, when you have a forming planet, okay, so this planet is, you will agree with me, has a certain mass, right? So it's not completely transparent for the disk. It has a certain mass, which can be even, up to several Earth mass planet, several Earths, or even larger. At some point, it will increase in mass. So it will interact with the gas and the dust around it. And to make the story simple, it will gravitationally attract the dust that is and the gas that is around it. Okay, so it will start to accrete matter. And this process of accretion is also done through what we call here, I didn't have the time to go into detail, you see the CPD here, the circumplanetary disk. Because what I've been talking about right now is the circumstellar disk, or the protoplanetary disk, but the planet itself is believed to have a small disk through which matter is accreted. And this process, of course, has to remove matter from somewhere. And this somewhere is the region around the planet. That's why basically at some point when the planet becomes massive enough, at some point it will form, actually, and this is seen both in simulation and as I told you, in observation, it will create a region where actually you have a less amount, it's not completely void, but you have lesser density of gas and dust as opposed to the outer regions. So because of the formation of the planetary core. So this dust depleted region is, we think, well understood, and at least as long as you trust this model of core accretion, that could be a nice explanation why the dust depleted region formed.
Thank you so much.
Very nice. Thank you. Are there any other questions from our committee? I think we addressed everything from the comments.
I think there are many questions because it's such an interesting topic, but I don't know if we have time for that or not.
Maybe one more.
Okay. So thank you, Dr. Labadie. It's such an interesting topic for all of us because it somehow connected us to origin of life. And I would say it was also kind of conclusion of our 1 year presentation, because we had exoplanets in the beginning, then molecular cloud, star formation nurseries, star formation, stellar evolution, and then you nicely take all together to bring us closer to the Earth, and that was very nice. Also, we had talks about black holes, and last year Nobel Prize, which also these high resolution infrared interferometry and adaptive optics resulted in that. So I would say it was kind of conclusion of 1 year, and
Thanks.
interestingly in our 1 year anniversary. So that was nice.
Happy birthday.
Yeah, thank you very much. So as I said, I have a lot of questions, but the first one I would like to ask when you are on this slide is that when you were explaining that, okay, there are two different scenarios at least about formation of planet. One would be the gravitational instability, and the other one would be these protoplanetary disks.
Well, that would be the core accretion
Yeah.
mechanism. Both are kind of using a disk, but with different mechanisms.
Okay, yeah, then this came to my mind that there should be also other process which result in that toward your end of the talk, you mentioned it can be also magnetic field playing a role. And then the question I have is that it seems simulations play an important role in understanding all these and put these together, because observation is kind of a snapshot. My curiosity, so I'm wondering if there is now a simulation that put all these together to answer how really planets are forming.
Yes, thanks for, I mean, this is a very interesting question. I mean, it's also a very large question. So I will not be able to, because of time also, to answer extensively, but what I will tell you is the following. So I think this field started, I mean, in a way, as often in astrophysics, I mean, simulations are always a little bit ahead. And, you know, like
Yes.
people have, I mean, I think we understand generally, I mean, not me necessarily, but people understand relatively well, I mean, what kind of physics can be treated. And the idea of doing simulation is not new. Simulations, of course, in star formation exist, as you already know, but also in planet formation. I mean, the first simulation, there are probably, I'm not even sure to be correct here, but, you know, like at least 20 years ago with SPH simulation, this kind of things, as soon as the computers were powerful enough to produce something. Now, to go a bit more to your question, there is certainly today, I mean, 2020s, a lot of people that have, or a lot of work that has been done in the area of simulation, trying to bring together also not only the property of the disk, but, you know, the presence or the existence of a magnetic field, the presence of vortices in the disk, the presence of a region that are called dead zone, where, for instance, the viscosity of the gas. Don't forget that all is about viscosity, right? Otherwise, the thing will never spiral inward.
Yeah.
So where the viscosity changes and so on. So people have, I mean, to be precise to your question, I mean, very advanced simulation have been indeed produced. And those simulations, they allow to understand, or at least to illustrate what we would expect from a time perspective. So how fast basically the disk would be consumed in a way. What kind of, on which time scale basically gaps may form or may not form. That depends, for instance, on, as I showed here, on the mass of the planet. What is the influence of the surface density distribution? I mean, because you have to imagine that those gas disks, they're not flat. You have typically more matter in the inner region than on the outer region, okay? How the influence of the central star with the irradiation, the strong irradiation of the central star, how this influence the disk, that is also simulated. So yes, I would say general question is that there have been a lot of work in the area of simulation of, you know, protoplanetary disk evolution, which has been extremely useful. And what I can say is that today we are in a in a time, I think it's a little bit golden era, I mean, golden age for that field at the moment, because I mean, everything comes a little bit together. I mean, this is really the first time that such detailed simulation can really be compared to detailed observation. You need to have, I mean, what I show here on that slide, I mean, probably this simulation was, you know, like 10 or 15 years ago. I mean, it took forever to observe really what happens here. So now we are living in the golden age where this effect are indeed observed and all this comes together. So I would say that generally speaking, we have, yes, did a better understanding thanks to simulation, thanks to observation, and thanks to instrument in particular, we have a much better comprehension of planet formation. I don't know if this answered really your question, but I mean, it was a general answer. I mean, the question also was large, so
Yes.
I mean, that's how I see it.
Yeah, sure. Thank you. And maybe the last question I get the chance to ask is, you talked about these central star should be in the main sequence at some point. But then I had this question. First of all, should the central star be in the main sequence to get a planet, to give birth to a planet or not? Then another question is that if that central star can be a binary or multiple star or not. So maybe these are also very large questions.
No, I will try to be brief because I know that you have also, I mean, other plans, but I mean, these are extremely interesting questions. So I still will try to be brief. So the first one is, does it need to be in the main sequence? So, I mean, here we go back to star formation, right? We know that basically, I mean, you know, star form from molecular clouds and so on, the contraction thing and so on. Then you have the evolutionary tracks, and it ends up to the main sequence, where basically is the moment where the star is ready, so to say. Okay, the star is ready, mature, and being in the main sequence essentially means, like for our sun, that basically there's no more disk. Okay, so what is left is the byproduct of potentially planet formation. I mean, is it sure that all stars necessarily have a planet around or several? I mean, this is still an open question. So your demand was, do you need to be in the main sequence? I mean, you cannot be in the main sequence to form a planet. You need to form that before. Okay. That's for sure. Because then it's too late. When you reach the main sequence, the disk is gone, pretty much, and to make it simple. So you have to start this thing, I mean, way before. And you have to start this when basically you are in the so-called pre-main sequence phase. So when you still have like a protostar, I mean, it's not a protostar any longer, it's a pre-main sequence star with a disk around it and gas. And there, that's the environment where you can build up your planet. By the main sequence, too late. So probably our sun will not see, I mean, unless we do not understand what's happening, but we will not see a new planet being formed in our solar system by any means. That would be very, very unexpected. Yeah. And the second question was, yeah, that's also, I mean, binarity. Binarity is everywhere in astrophysics, right? I mean, it's absolutely a central topic. So yes, disks are absolutely found around binary stars. Actually, I can tell you that planets are found around binary stars. Now, the big question is does it form the same way? I mean, there's good hint for the moment to believe that it's not that much different. The big difference, of course, would be on the property of the binary star itself. And I will close with that, is that you can imagine that if your binary is very eccentric, means that, so I try to do that with my fingers. So basically it has a very eccentric orbit. The, I would say, interaction with the disk will be very, very different from the case where the binary has zero eccentricity.
Yeah.
Zero eccentricity, basically it will leave the disk not too much altered. When it's very eccentric, it will kill the disk kind of much quicker. So on top of the normal disk dispersal that you naturally have because of accretion and so on, the binary will also contribute to kill somehow your disk or to reduce the lifetime of your disk, which of course will have an impact on planet formation. But this is also topic under study.
Okay, thank you.
I think I would have a follow-up question to this.
Yes.
If you don't mind. I know we are low on time, but
I'm fine. As long as you're fine, I'm fine.
Yes, Professor Labadie is here, so I have to catch him. There are certain phenomena happening also in these environments. I don't know if you already mentioned it, but there after accretion has already started, there's a phenomena called Herbig-Haro objects around the stars, which means just for the viewers that while this accretion is happening, there would be a jet perpendicular to the plane of the star, and they are basically jets spewed out by the star and creating shock waves around, maybe also helping star formation in that nebula. But are these objects of your interest, and do they have any impact on formation of planets, and also maybe in binary systems they do something interesting?
Yes, very good question. So first of all, am I interested in that? Yeah, I mean, I'm interested in many things. So of course, this I find interesting as well. I mean, the point is, can we do everything? So, I mean, we actually try also. So this is more a question that is a bit more connected to star formation rather than, you know, really planet formation. But I mean, somehow it's connected. So yes, we do also study with interferometry. We study the gas around the stars and how the gas actually evolves. And as you perfectly said, it is known that in this problem of you know, angular momentum, the problem of angular momentum concept. So basically, you have to lose angular momentum in order to advance in the star formation process. Jets indeed play a significant role, and Herbig-Haro are just a signature of those jets. Okay, it's just an expression, so to say, of those jets. So they are seen. They are. We think that they contribute to remove angular momentum from the system, and therefore allow also, you know, continuation of accretion and so on. Now going back to planet formation. I would say that also I'm not completely sure here. So I would say, from at least my point of view and my view on this, on the state of research, I would tend to say that the jet doesn't seem to have an immediate and direct impact on planet formation, which doesn't mean that it's not somehow relevant to planet formation. But, you know, like those are typically very collimated jet, which tends to be perpendicular to the disks, you know, which is different, for instance, from an outflow, which is, you know, less collimated and can impinge on the surface of the disk. Okay, then of course you may imagine that those outflow may somehow interact, and we see that in H2, I mean molecular hydrogen images, we see that basically this outflow interact with the disk and basically excite the gas. The jet themselves, they tend, and that's how we find them, tend to be perpendicular to the disk. So I would tend to say that, I mean, at least on the first order, they don't have an immediate impact, or at least an immediate, I would say, interaction with a planet being formed. But again, I mean, one has always to be cautious a little bit with that. I mean, if that is not relevant at all, I cannot say. It could be that, of course, this is still relevant, because, I mean, depending on how quick you remove the angular momentum, maybe, you know, your disk will disappear very quickly. So in an indirect way, well, this may have an impact anyway. So that's what I can tell at that point.
Thank you. Just as a lighthearted additional question, Professor Labadie, do you, after all these years of experience in astronomy, do you call your room after you clean it a dust depleted region? You don't have to answer that.
Well, I mean, what I can tell you is that our institute is certainly not a dust depleted region. Okay? It's full, and I mean, first from the ceiling, I mean, they have to renovate that since years. So, I mean, no, it's not a dust depleting region. And I'm not really fighting against this, because it would be, you know, accretion is too, I mean, fighting accretion here is too complicated. So I'm somehow part of the accretion process here. That's unfortunately, that's the way it is. I hope it's not too bad for my health, but that's the way it is.
Well, at least we hope that some stars are born in this process. But
very nice.
Thank you, Professor Labadie.
Thank you very much. So I will stop sharing if I understand. So
sure.
Okay.
Sure. Thank you very much for all of the explanations.
Good.
As you can do, like, it was a wonderful presentation.
My pleasure.
Sorry if it we didn't let too long. If you didn't explain everything that you wanted to, but as you can tell, we have a lot of questions, and you could be here for days if you answer all of our questions. So thank you very much for your explanations. That were wonderful. So thank you very much.
So I thank you very much as well. I mean, for inviting me. I mean, for the questions. That was very nice experience. And yeah, so I think I will disconnect now, and I will say bye-bye to everybody. Thanks for the attention, for the questions, and yeah, I'll keep on going with this initiative. I think it's very useful and very nice. And you know, you should spread the word and invite also. I mean, the people will come. So it's very good, I find.
Thank you.
Thank you.
Thank you very much, and have a nice evening. Bye-bye.
Thank you. Bye.
Bye.
And now we have our news segment with Parade, as normal, I guess, right?
Yeah, and but before that, I was hoping that we should already warn Professor Labadie that we will write all the questions on letters and send all the mail to him so that he receives it, and at his home, not as in the office. But yeah, yeah, but yeah, let's go to our segment about the news this month. And well, I don't know if nerd is still a cool word, but yeah, let's, after this nerd chatter with Professor Labadie himself, we will discuss some news this month. And for that, let's start with Hubble troubles. I don't know if you heard, but the latest news from the Hubble telescope, the Hubble telescope, is that there is another glitch. Sorry that I sound like thankless about this magnificent orbital observatory that has fed us with the most beautiful pictures of deep space. But you have to understand, I'm just another astronomer, innocent astronomer who likes that their telescope computers keep working, because someone like me might have spent months on writing a prestigious proposal for the Hubble telescope, and now they have to sit back and relax and think like, why is it still like not easy to go to space? You know, that way they can just at least smack the telescope a couple times. And most of us know that this is the proven scientific way to make instruments work again. Don't tell me you haven't tried. If it was a programming issue though, which it also is kind of at Hubble, things would be different because we would all know what to do. We will just, fire up Stack Overflow and find the error and fix it. While we're doing that, we will binge on ice cream, sleep, and run the code tomorrow, because today it will not work. That also makes me think, well, do space agency programmers also regularly check Stack Overflow? Because that would be cool, right? Like, to accidentally stumble upon a post saying, oh, can somebody help with the Fortran, please? I need to fix this Hubble telescope and my boss is getting angry. But before I move on, I should tell you what I was actually talking about. So the Hubble telescope is in safe mode right now. As you can see, I have illustrated what safe mode is. Of course, you know this from early years of the BIOS system. And NASA is getting busy troubleshooting the 1980s computer because the Hubble telescope was launched in the 1990s. So the technology was even before that, dated before that. Initially, this was thought to be Hubble's-Eimers, which means it's a memory error. It is officially not called Hubble's-Eimers. Please don't use that term, but let's popularize it. But now the focus is on interface and central processing modules. Hubble does have a backup computer installed, by the way, as all things in space have a backup, except humans. So they were installed by astronauts in 2009. But at the same time, the gyroscopes are acting up, and even some backup modules are acting up. So you never know when this just switches off. But we still love the Hubble telescope. Anyway. The next big news is, do not allow Jeff Bezos to return to Earth. This is not news. This is a petition, of course. So I don't know, again, if you've heard this, but on the next suborbital flight of Blue Origin's new Shepherd telescope, there's going to be a very expensive passenger the CEO of the company Amazon and also of Blue Origin, Jeff Bezos. The title here refers to a petition on change.org. We at AoT Koeln do not have an official opinion on this yet. We will soon have that, I hope. Maybe after I tell you guys about this, we will have a discussion and a debate, and we will see what you think about this. But right now, I have the screen, so please lay low. Anyway, the petition says billionaires should not exist on Earth or in space, but should they decide the latter, they should stay there. I would say touche to the billionaires. The petition was already signed by almost 150,000 people. Well, interestingly, Jeff Bezos, again, the Amazon boss and career billionaire, is scheduled to take a suborbital flight aboard a Blue Origin rocket. I already told you, which is his own company again. And this is soon, July 20. So since this is soon, I would like you to know what a suborbital spaceflight is, which is a spacecraft, which is when a spacecraft reaches outer space, but its trajectory sort of intersects the atmosphere still, and the surface of the Earth. It goes above enough that it is very much away from the surface of the Earth, but it will not complete a revolution around the Earth or reach escape velocity. So it will still reach outer space, which means that outer space is defined generally from an altitude of 100 kilometers, which is also the Kármán line above the sea level. But anyway, that is science, which is good. This petition was started by some guy called Rick G of the USA, and I already told you what it reads. Well, he started this as a joke, and I have a hard time to decide who the joke is on, because the petition very quickly reached approximately the number that they were targeting, 150,000 signatures. But this is, as you know, just a fraction of the number of people trapped in the company Amazon's monopolistic loop of doom shopping. I know all of us have been there. And Jeff Bezos has probably laughed it off. Like he doesn't care about 150,000 people. And I'm sure these laughs are very similar to the bouts of ironical laughs he has, having named his thriving company after a dying, dense tropical ecological biome, otherwise called a forest, otherwise called the Amazon forest. But we scientists are obviously in awe of the rapid technological development started by these private space companies. Of course, we love what is happening technologically. We love what the spectacles that we get to see when people are launched to space very regularly now, and that's good. But this we have to understand. This is of course built on the back of poor warehouse workers. I'm specifically talking about Amazon, who are forced to time their bathroom breaks and be human robots to get us the next day deliveries. I would personally like space company bosses to keep referring to habitation in space as colonization, because that's exactly what they seem to be doing anyway. Colonize, expand, colonize, expand. We all have to work for the greater good, but we all have to work for the greater good of the billionaires, because the greater good of the poor warehouse workers does not matter, and it's not visionary. The point is, colonization is bad. We have to explore, we have to respect, we have to be excited, we have to have wonder about things in space. We don't have to colonize space. Well, yeah, sorry for changing your mood. But some better news. Some news which will actually make us astronomers happy, though, is that the square kilometer array finally begins construction. Yay. This square kilometer array is set to become the largest radio telescope ever built, and it will finally commence after 30 years of preparation on July the 1st. I guess today, I didn't confirm, but that's what they said yesterday. instead of relying on a single extremely large dish, it will consist of a precisely designed network of dishes and antennas distributed across 2 sites. So the SCA mid array will be in South Africa with 179 dishes, each 15 meters in diameter. And the SCA low array, which is going to listen to low frequency bands, will consist of 100,031, sorry, numbers. 131,072 antennas located in Western Australia, north of Perth. I guess we just discussed with Professor Labadie how it works. There's going to be interferometry, of course, because this is not a big single dish. We will have many separate dishes interacting with each other, getting the signals, and the signal is processed in a way that it all acts like a big telescope. But this also seems to me like a pop culture coup, because ska is also the name of a genre of music which originated in Jamaica in the 1950s. I have been to ska concerts, but I didn't know one day it will be a concert of notes and colors of the universe. I will definitely do the ska one day and brag to my Muggle friends, because I hope we organize a trip to the ska telescope, right? At least the site where it'll be built. Ideas. Anyway, last month, we attempted to popularize the then upcoming solar eclipse on the 10th of June, but our hearts were already pre-broken since we did not expect to see the spectacular sight. Also, since Craig did not manage to arrange visas for us to go to the Canadian Arctic, Craig.
Sorry.
But everybody's nodding, by the way, if you can't see all of the people here, my colleagues. But before I could complete last time, I was cut off by my nice colleagues, also Craig, because what I actually wanted to say was that not just that the June 10th eclipse would be in a country not at all near you, but you could still spot the annular version, which is also good, which we also had fun doing. That also meant that we could still see the eclipse from Europe, where we are, and an annular eclipse is okay, well, not that interesting maybe as a full eclipse, because there won't be like a complete darkness sort of environment, but it's an eclipse nevertheless. We are still interested. Some weird stuff happening in the sky. But before we recount the good memories of the day, I bring you the tweet of the month, which also has a very exclusive, clear, crisp view of the eclipse, with all the necessary precautions haven't been observed in taking the picture. Brace for it. Very beautiful picture. You have never seen this kind of picture before. Yeah, this is the view of the eclipse from Garching. The tweeter Juan Carlos Munoz says, "Amazing what cell phones can do these days." I am hoping that Mr. Carlos Munoz is maybe one of our colleagues from the Astronomy Institute, Extraterrestrial Astronomy Institute in Garching, but I can also confirm that my smartphone is not that expensive to take these kind of nice pictures. But Mr. Munoz just hit it out of the park, I guess. This eclipse is also very tasty for some reason. Anyway, well, while Mr. Munoz was having fun with his sun cookie, we were busy making our own observations. By the way, I'm sure he also took nice pictures. I'm just saying that we also took nice pictures, and we were busy making our own observations of the eclipse in the garden surrounding our University of Cologne. And here's a glimpse of the stunning pictures. And these pictures are taken by our colleague Sajjad Mahadizadeh. Sorry for the pronunciation. Very nice pictures. He was completely at it. I'm sure you guys have lots of memories to recount from that day. But before you do that, I will show the memories. And while Sajjad was, you know, busy using his talent in actual photography to take these pictures, we were busy trying to get an impression of the eclipsed sun in the form of shadows. It was fun to play with the sun. Not only that, we even made tutorials for our Instagram followers in the interest of safety, of course, to show how we should wear glasses on our eyes. I hope I have the video here. Okay, I do have the video here. On the left, you can see us. As you can also see, we are maintaining social distancing without, Craig even has a mask. And yeah, I hope you learned a lot from that video. This will probably be the last slow motion high octane movie made of me ever. Thank you, Alina, for doing this. But on the right, you can see that there's Roya and Sajjad down under the camera, trying to get a good picture of the sun, and they did, as I just showed you. What do you think about these guys? How do you remember the day, and are you still excited about that day, or maybe about the next eclipse? Roya, you are in the picture, so you have to say something.
Yeah. Which picture? On the left, I'm blacked with another solar eclipse.
I'm sorry
yeah.
for that. I just edited it, so.
It's fine. It's also kind of fun. Yeah, I'm so interested to experience also that solar eclipse that you already showed, although it's not complete, but this ring shape structure also is fascinating, and I hope that sometime we can see that. Yeah, maybe next time Craig can provide us ticket to somewhere to observe, right?
I was just asking for the visas, but tickets also sound good, actually. I would also like some tickets.
I guess you assume that I'm rich or something.
I mean, you're from there, so you have some responsibilities, Craig.
Inside connections.
Yes. I mean, solar eclipse science could be still interesting because, as Professor Labadie also showed us, that we have coronagraphs these days, which started off as something that we used to eclipse the sun and observe the corona, but now we can use them to observe exoplanets and also star formation disks. So yeah, this some stuff from olden times might not still be useless. Please keep using it. Alina, I'm sure you blocked out Roya in that picture because you were. I wouldn't like to assume, but was it because you were not in the picture also?
Yeah. Well, how can you find out all these sensors?
I know what you feel, Alina. I'm just.
I'm so sad. Yeah.
But thank you for taking amazing pictures. Thank you everybody who took amazing pictures. Yeah, with that I hand this mic, Zoom mic back to Craig, and Craig has fireworks. So
yeah, who is by the way celebrating something like a 1 year anniversary, I guess.
Yeah.
I think you have to stop sharing for it to be visible. Yeah.
Yeah.
Oh,
No, I forgot to put this on earlier. This is for the 1 year anniversary tomorrow. The 1 year anniversary since we started streaming. So celebrate that. I guess also technically today is Canada Day. So
awesome.
Cool.
I completely forgot about it though.
Okay.
Preparing for this.
So that's the real reason, right, Craig?
One of the reasons. I don't know. Pick one. But yeah, it was a very nice event today. Thank you everybody for their contributions. And let me just check. There's no more questions. Still a few viewers, so that's good. So thank you everybody for sticking through the entire event. All of the questions for Lucas Labadie. We could go on for hours and hours, but we have to end at some point. So thank you, and thank you for coming to our 1-year anniversary. And yeah, I think we'll take a break next month, but we'll be back in September with Andreas Gukis, and you'll learn more about what the next event will be on our social media pages, Facebook and Instagram. So thank you.
Thank you. Bye.
Thank you so much. Bye.
Bye.
Bye.